So the lecture that I want to present today is recycling and recovery of metals from urban resources. So as we go along, you will see that the area is actually pretty wide, pretty big, and also can be categorized based on what types of urban resources we are talking about. The reason is that every types of urban resources may have different composition, which means that when we want to recycle and recover metals from that particular resources, we will have a different approach, right? Different metallurgical approach. But the key things, as I will show you a bit later, there are similar approach overall, but in the end, which is in the metallurgical aspect, in the metallurgical processing, there may be some differences depending on the chemistry of the materials. So yeah, so thank you very much for the introduction. So I don't think I should explain this again. But yeah, and also about my research as well. So there are a number of areas. Urban ore processing is one of them. There's also decarbonization of metals and mineral processes, hydrogenation, and also a reduction of carbon in the processes, for example, solar metallurgy and also astrometallurgy. Maybe I just explain a bit about my campus. So I'm from Swinburne University. So Swinburne University is actually in Melbourne. So that is in the southern part towards the east, so southeast part of Australia, in the corner there, and it's a very nice city. And it's also called Education City because we have 7 universities in Melbourne, and they're pretty nice city to live and also to study. And Swinburne itself is located in Hawthorn. So Hawthorn campus is the main campus. It's about 10 minutes train ride from the city center of Melbourne. So we have our own train station, which is Glenferrie train station, which is in the middle of the campus itself. So the campus is quite compact, modern, and with everything actually nearby. And I believe Professor John Holley also has visited Swinburne as well. So it's been a while. So yeah. So this is just some of the snapshot of some of the building in Swinburne. So on the top left here, it's called the Advanced Technology Building. So we call also this Lego building because it looks like Lego. And my office is in level 8 of that building. Right. Okay, so let's go into the content. So the basis for this lecture is actually in the context of circular economy and also resource efficiency. So these days, there has been a lot of emphasis on these two areas because first of all, it's important, right? And also the fact that when we make things, when we produce a product, right, and also at the end of life, we actually are generating waste. So as much as possible, we want to be able to process this waste. There are also additional rationale. For example, here, first one, there is a significant lowering of the grade of ores around the world. So when we, let's say, plot the purity or the the grades of ores, let's say from 1800 until now, there is actually quite a good trend downwards, right? So clear trend downwards. So so that's showing basically the concentration or the grade of ores declining around the world. Of course, part of that reason is because we mine the good ones. So the good ones we mine, and then we extract the metals, which means that we left with the deposit that has a lower grade. That doesn't mean also there could be other deposit actually with some good grade of ore, but in general, it's actually declining. And if we relate that to what I said earlier, there are also other sources of metal which is coming from waste, right? So and we call that urban ores. That comprise of a lot of things. Well, we say urban ores is actually ores that already above ground, right? That you can find in urban setting, you can find in city, you can find in industry, right? So so that's why here, for example, we have industrial waste can be categorized as urban ores, consumer and household waste, construction waste, and end-of-life products, and also electronic waste. So, so these are considered as an urban ores. And as we look at later on, the characteristic of urban ores is very complex, and it's as complex, or even actually more complex than low-grade or weathered ores, right? Which means that it requires some extensive processing. So just talking about this urban ores, this is an example on the right-hand side. You can see in here on the top left here, there's a mobile phone waste. There's also battery waste, solar panel waste, end-of-life magnets waste. So all of these have different chemistry, have a different chemical system. So so we will need to think about the appropriate process for each of these, unfortunately. And in the context of today's lecture, I will be focusing more on the waste PCB that can be get from the mobile phone or from other electronics. So, but the broader approach will be the same, but the detailed metallurgical processes afterwards may be different later on. For example, if we're talking about, or we're comparing between waste PCB and solar panel, or with batteries, for example. In general, electronic waste is generated about 50 million tons annually, globally, around the world. And this actually, from one side, is actually a great challenge because we need to process it. But also it is opportunities because as you will see in the next few slides, that it contains some precious metals, it contains platinum group metals, in addition to base metals and also rare metals. However, it also contains some hazardous elements as well in some of them, which we need to also consider to process. There's also another thing. This e-waste considered hazardous, so we cannot really just put it in the landfill, because when it leach out, and there's some hazardous elements coming out, and then it goes into the ground. Right? So so that's what it also means by great challenge there. Okay, right. So, and this is also connected with the what is called the Sustainable Development Goals. Yeah. So you probably already seen this many times, but I think it is good because we have some sort of agreement, around the world globally, that's we want to do good things on Earth, right? And there are clear, goals. There are 17 of them, and the context of my lecture today is related to the goal number 12. And some of others as well, but mainly in the goal number goal number 12, which is responsible consumption and production. Yeah. So yeah, and if you try to find the details of each of the goals, you can, and there's a more detailed explanation, and is very specific as well. And if you are eager to find out more, I think you should try to find that in more details. But specifically for the goals number 12, it actually mentions specifically about electronic waste. Yeah. So it mentioned that electronic waste actually grow by about 40% every year, right? And between 2010 and 2019, that this waste, yeah, only about 20% is recycled, right? And in the past 5 years, this number is increased, yeah, but still it's not to the level that quite significant. So there are many reasons of that, and as we progress through the lecture, you can see how complex it is and why it's not actually processed more. Yeah. Just some other aspect about goal number 12. There's about fossil fuels and fossil fuel subsidies, which are also contributing to the climate crisis. So that one also something that mentioned specifically, and also some loss in the food in supply chains, for example. That's also needs to be reduced. So among other things as well. So yeah, again, if you're interested in looking at each of the goal there, you can, and it's very interesting and it's very to the point. Yeah. Okay, so let's go in more details about the e-waste. I think it's good to start to define what e-waste is, right? So this is quite interesting because the definition of e-waste is actually pretty big, right? It covers pretty big types of material. So the European WE, so there's WE here. WE is called is basically waste of electrical and electronic equipment. It's basically e-waste. But other words of e-waste is WE. It is from the European directive. It's defined as electrical or electronic equipment, which is waste, which include all components, sub-assemblies, and consumables, which are part of the product at the time of discarding. On the other hand, Basel Action Network define e-waste as this one here. So e-waste encompasses a broad and growing range of electronic devices, ranging from large household devices such as refrigerators, air conditioners, cell phones, personal stereos, consumer electronics, to computers, which have been discarded by their users, right? So as you can see, the definition is pretty wide. And if you look at refrigerators, so the material in there's a lot of things in there, right? So you have the steel plate, you have the plastic there, and maybe some electronics as well, not as much, but some electronics in there. And glass, of course, and that's completely different than air conditioners, completely different than cell phones, personal stereos, and others, right? So sometimes when we talk about e-waste, let's say if you write papers about e-waste or read papers about e-waste, you will need to check what does it mean by e-waste in that context. It could be a very specific aspect, just waste PCB, for example. It could be the whole mobile phone, right? It could be the whole bigger, there's also another thing. For example, in mobile phone and in laptop, there is battery as well, right? So battery sometimes included in there as a as e-waste, right? But but it has different ways of processing there. Right. So in general, now when we look at the traditional material cycle, we have a cycle where we start with digging some materials from underground, right? So mining, yeah, and then we process the mine materials, we beneficiate it, and then you can then go into mineral processing, basically to beneficiate your minerals, and then you extract the metal. From metals, you make an alloy, for example, into engineering materials, and then you make up a product, and then the product goes into usage time, yeah, and then at the end of life, we previously mainly put the product back into landfill, right? So it goes circular like that. And similarly, when we're talking about processing of these urban resources, we call it urban mining, right? So so from the product that we use in the traditional material cycle, yeah, so this one here, we after their end of life, we go into this cycle here, right, where we mine them. So we take those products, right, and then we do this processing, physical processing. So we will be discussing this in a bit more detail later on, right? So this physical processing, or similar to beneficiation, um, in the case of traditional ore, we do that, and then we get some fractions, and that fraction goes into metallurgical processes, right? And then we can use that metals back into a production of a product, right? And then it goes into this one again. So this is sort of a modification of material cycle, a traditional material cycle, where the source is actually from the ground, right? The traditional ores, but in this case we use urban ores. Yeah. But the idea is similar, and we also want to do this in a circularly. Now, one of the key drivers of circular economy is metallurgy and recycling. So we need to know knowledge about metallurgy, among other things, and also knowledge about recycling, right? And as we go along later on, you will see that consumer products are quite complex. It consists of many technological and critical and functional materials or elements, and we want to be able to deal with these complex materials. Just to give how big and how valuable, in essence, these resources. So if we're talking about my wedding ring here, so I have my wedding ring now. Now it's actually not in the in this finger anymore. Now it's in the pinky finger because I gained some weight. But anyway, wedding ring. So wedding ring can contain up to 2 grams of aurum of gold. Yeah. So of course this wedding ring is very expensive. 2 grams, a lot of gold there. So these 2 grams of gold in my wedding ring, right? You can get them from about 10 to 15 kilograms of mobile phone waste, right? So 10 to 15 kilograms. So that's not, that's not much, right? 10 to 15 kilograms. And the fact that, mobile phones is already there, above ground, you don't have to mine them. So theoretically, or naturally, you think that it will be quite easy to process this and to get this, right? But yeah, but if you compare this with the actual ore that we need to do, or we need to process from underground, you have to actually process about 0.5 ton to 1 ton of ore. Yeah. So as you can see here, the scale, right? And of course, processing this 1 ton of ore, it takes a lot of a long route, right? And it will also uh, you know involve a lot of energy and that kind of thing. So that's also another thing. Some in general, when we're talking about recycling of metals, especially base metals from urban ores or secondary sources, the amount of energy, usually the amount of energy is actually much lower, right? Only in some situation, um, including e-waste actually, you can actually have large um, uh, consumption of energy and costly. Yeah. So, but for example, if you want to make aluminium from aluminium ores, such as bauxite, for example, yeah, and comparing to getting aluminium from remelting, recycling aluminium can, for example, soda can, or Coca-Cola can, for example, the energy requires only 1/10 of the processing original ore, right? So that's another aspect. So why we want to recycle. Yeah. So yeah. So just to give also a different perspective, from 1 ton of mobile phone waste, it contains about 200 grams of gold, right? 3 kilograms of silver, 100 kilogram of copper, and 100 gram of palladium. But this one is not all. I just showed 4 elements here. There are actually more than that, right? So that also some consideration whether you want to recover everything, right? Or you want to just focus on the key valuable metals, right? Because it's all about a balance between the economics and also balance with the the value that we get and with the long sort of process and so on, right? And the energy as well. Right. So now this is quite interesting table here. So this is actually contrasting the composition of different types of e-waste, right? In terms of weight and in terms of value, right? So, so we have information here from TV board, PC board, mobile phone, portable audio, DVD player, calculator. Now, let's just focus on mobile phone, right? Now, in terms of the weight distribution, right, about 56% of mobile phone contains plastics. And you have about 13% of copper, 5% of iron, 1% of aluminum. This is in terms of weight, yeah. And also ppm of silver, let's say 1,300, gold 350, palladium 210, and there are also other elements at ppm level, right? So the amount of in terms of weight of the silver, gold, and palladium is less than 1%, right? But if we look at this from the perspective of the value share, right? So in here, we compare in mobile phone. Now, the value of the sum of the precious metals, gold, silver, palladium, and others, right? That not included in here. It contributed to about 93%, right? For the copper, it's about 7%. And iron and aluminum, we don't really count them because it's basically not valuable compared to the others, right? So you can see the contrast here. So you can see that we want to get this small amount, which is quite precious, and it's not easy to get that small amount. Yeah. This is also just to give some context as well of the value of those metals. So presented in a different way. So for example, here, um, um, we compare this. We try to calculate the value by connecting it to the price, right? So, for example, copper, the price is about 7,000 US dollars per ton, and palladium 40 million dollars US dollars per ton. Gold is 21.7 million US dollar per ton, and so on. Now, if we consider the weight of this element per pound, so let's say you get this 16 grams of copper, 0.35 grams of silver, 0.034 gold, 0.015 palladium, and 0.000334 platinum, totaling about 16.4 grams. So if we times that by the value, right, and we'll see that in here, gold price or the gold value and also the palladium value, that's really big, 738. Sorry, this is per 1 billion pounds, yeah. So we times that weight per 1 billion pounds. So you can see the value is 738 millions US dollar for gold, and 608 millions US dollar for palladium, and the total is 1.6 billion, right, per 1 billion pound. Now, currently, around the world, typically about 1.5 billion mobile phones sold every year, and of course, the life of this usually between 3 to 5 years, right? And at any one point, over 5 billion people have a mobile phone. Some of them have two, right? Or even three. So you can see and you can sort of predict. So every year there will be like mobile phone that reach their end of life, and we will need to process that basically. Now, when we're talking about when we discuss about this, it is important also to know what is out there, right? And that amount of 50 million tons generation every year is for all around the world, right? And also it's quite that's an estimate, but it is also important to know locally. For example, in Korea, or in particular, or maybe in Seoul, on one municipal, how much is e-waste generated every year, right? The reason is, this one is the solution for this one is actually multifaceted. Yeah, we will discuss about that later. But if we know how much out there, we can plan how we will be processing these materials. So this one is some of the work that we did a few years back. We're trying to quantify the e-waste generation in Indonesia, and I believe there's also some papers focusing on Korea as well. So if you try to find literature search of the paper, I think there should be some work in that aspect. So in here, we try to estimate and forecast the e-waste from IT product. So there's a PC desktop, there's a laptop, mobile phone, and tablet. So we're focusing on that one. And we predict from 2020, for example, in the case of Indonesia, there's an increase of e-waste, let's say in 2025, which is this year, now about 150 million units, yeah, of this product, yeah, and it's increasing significantly, or in a large trend there, up to 2040, estimated to be 270 million units, right? E-waste unit, or e-waste from this unit. In terms of weight, yeah, so we also try to calculate that. So from 1990s and predicted to 2040, and you can see here in, let's say, 2040, it is estimated that the total e-waste generation in Indonesia each year will be 3.2 million tons, and that will correspond to about about 10 kilograms of e-waste per person annually. And I should mention this work is underestimated. So we took we rather have the lowest number. So, but in actual is actually more than this. Then we also try to quantify what is the value, right? So the value estimated in 2040, for example, here, we will have about 800 tons of silver, about 400 tons of gold, and sorry, 400 tons of palladium, yeah, and then about 200 tons of gold, and about maybe 100 tons of platinum by 2040. Right? And if we convert that into value, economic revenue in terms of billion, then by 2040 in Indonesia, the potential economic value of these resources is about 15 billion US dollars. Again, it is underestimated. And this is just in Indonesia. And if you think about Korea, Australia, and other places, so so the value is pretty big there. So it's something that drive people to process it. It is also good to know, for example, where are these e-waste located. So based on the population and other aspects, so we developed this map, and mainly, for example, the e-waste generation occur in the main island, which is the Java Island, that one there. Which is about 105 to 362 kilotons every year. I think this every year. Yeah, every year. Yeah. So and then next one is in Sumatra and in Borneo, and then the rest of the islands. Yeah, I would actually love to work on this in the context of Korea. So I'm just curious, maybe there's hasn't been done, but could be it's already done as well. Anyway, okay, so that's just, so it is important to know, first of all, how much is available out there. So that's why we did that study. But yeah, so I will go back into that later on. So let's go into details about the e-waste and the e-waste characteristics. So for example, this is just showing some construction of a Samsung Galaxy phone. So you can see there's some plastic, maybe the back end there, right? And ceramics for heat sink or so on. There's also metal chassis, right? There's also a bit where you have the electronics, the PCB, right? And the cabling, right? And also you have the screen as well, right? So, and also you have the battery. So, so in here, usually the battery is processed separately. So when we try to process e-waste, let's say mobile phone, you separate the battery into a different processing line or processing route, and then you, in fact, actually, most of these also will be separated at the beginning. So as much as possible, plastic goes into plastic, for example, screen goes into the screen, and waste PCB goes into waste PCB, and so on. So as you can see, just want to show you, it's quite complex, right? And it's not just that, the components are very small. So if you want to separate them to small scale, it's also quite difficult there. So this one, just a different one as well. So on the right hand side is from iPhone. Same thing. This is the waste. So this is the PCB, for example, and you have the small components as well, which is very small. Now, because I also mentioned about batteries, the batteries construction is also quite complex as well, right? So it contains different layers, different components. Like for example, this one here, a sample that I'm showing here, you have a cathode layer, right? And you have separator, which is made of different metals. You have the anodes, graphite in there. So the cathode itself, in this case, is lithium cobalt oxide, lithium manganese oxide, but there are different types of cathode materials as well. NMC and LFP, for example, and so on. So different chemistry. And this is folded into the case, metal case, and there is plastic as well. So it is also quite a complex there. Right. So as you can see from those two examples, the e-waste, characteristic of e-waste, in this case, waste mobile phone, waste PCB. First, it has quite a complex microstructures, right? So as you can see, as I mentioned before, it contains remarkably different components. You have plastics, which is made of hydrocarbons and some other elements in there. You have glass or oxide, for example, the touch screen. Now, even the glass itself is not just a regular glass, right? So you have a thin layer of indium oxide, right, which is quite valuable as well. But it's only thin layer, right? So even the touch screen or the screen itself is made of different types of glass and layers, and there's some valuable elements in there. Of course, you have metals, which is from ferrous and non-ferrous. You have this copper and the valuable metals, and so on. Right? It also has complex compositions. So the metals of interest are usually in minor proportion or very low concentration, as you saw earlier, right? It's in 1 ppm or not 1,000 ppm or hundreds of ppm level, or even in tens or 50s ppm. So it's a small, low concentration. So it also contains large number of elements, which include valuable and hazardous substances. So if we look at cell phone, there are more than 40 metals or 40 elements on a cell phone, right? So it's coming back again. Do we want to recover everything, or do we want to focus on the valuables only? Another problem is that the composition, it varies for different products, right? And also with different time. What I mean by time is, technology evolves with time, right? So for example, the concentration of a gold, about 300 ppm, that is actually coming from the old mobile phones from about 20 years ago. Right? So, but the modern phone these days will have smaller concentration of gold, but it has more variations of elements in the modern cell phone. So and of course with different products, it has different composition. So we need to have quite a robust processing methods. Yeah. So that's some of the takeaways from this. So this is just also to illustrate how complex and how the modern sort of technologies that we use these days, it contains of more than 40 elements, various elements. So for example, in the context of energy generation, in the 1700 we have windmill. Yeah. So this windmill is to convert wind energy to mechanical energy. For example, if you want to crush grain and to process your barley, or so it's for food processing, right? So we use this. And on those times, these are made from only 6 elements. You have lead, you have carbon, zinc, iron, copper, and tin, right? And with time, talking about heat engine, right? It becomes more complex, more elements in 1800. automobile in 1900, you have more elements in there, and the more modern energy products, such as wind turbine, similar wind turbine, yeah, from 1700 to 2000, but slightly different purpose. So of course, this wind turbine, we use it for converting wind energy into electricity, and in doing that, we use electric motors, right? Which need some permanent magnets, so which has a lot of rare earth elements in there. So in this one, you have cadmium, ruthenium, palladium, iridium, rhenium, platinum, wolfram, gold, silicon, magnesium. It's basically a lot of elements in the periodic table. There's also rare earth oxide and so on. Right? So it becomes more complex and more complex. Now, having said that, we also still learning about this one. So there are also technical challenges. First, there is a limited fundamental knowledge about these new complex materials and how to effectively process them. Right? So information about thermodynamics, yeah, information about kinetics of separation, refining process, extraction process, and in general the materials itself, right? Um, so we still developing a lot of this knowledge, right? There has been some significant progress, of course, but because it's just too complex, we still need to do a lot of stuff to 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 fill our knowledge there. So there's also some challenges in terms of general processing and also processing route in terms of technologies as well. So because it's quite complex, then you will also need to have quite a extensive pre-processing, and also the overall process route as well become quite long, right? If you want to separate each of the elements, everything, for example, it will be very long process. So it is also combination, between the economics and the practicality and everything. Right? So there's still a need to develop new processes or at least modify the existing process or technologies. And this is another thing. We want to make sure we do it in a sustainable way, right? So it's not just economically good, but also environmentally also acceptable. I think that's the difficult part there. So in addition to this technical and the processing aspect, you will also need to know about some techno-economic to evaluate whether one process is good or not, right? Combine that with life cycle assessment, right? Because we want to know whether our process, how much actually impacting the environment, right? And usually, of course, some of these process actually develop only in laboratory size, right? So we want to increase that into full size plant, and the full feasibility of the process need to be considered, which include this techno-economic and life cycle assessment. So for those of you who's not familiar with this one, techno-economic, basically it's as you can guess from the words there. So we are evaluating the economic of the process, and that's trying to consider what's the cost of the input, cost of the process, a lot of things, to run the process and so on, and then to produce the product and what is the value of the product, and you try to do economic assessment and try to find out whether that process is giving you a benefit economically or not. So that's techno-economic. And LCA, or life cycle assessment, is actually a procedure, or it's an approach for us uh, to evaluate the impact of the process to the environment. So it includes defining the boundary of our process, analyzing what's the input and the output, the emission, the CO2, and so on. So usually the number of key things that they analyze in life cycle assessment is the energy uh, requirement, right? And also the CO2 emission, for example. That's the two big things, energy and CO2 emission. But sometimes when you do a detailed life cycle assessment, it can go down to what is the amount of chemical that goes in on the ground, on the to the atmosphere, right, to the water, and so on. Right? So that's quite a involved procedure as well. But also there are non-technical challenges. So what we talked about previously there is more like technical engineering, but there's also non-technical. So I mentioned about economic, yeah. So the overall economic of the process usually becomes the main driving force, whether some materials are processed or not, yeah. Sometimes we will need to have new or innovative business models, right? That need to be developed to shift towards more economical process. So, for example, some of the new business model now these days, actually, you are not in some countries, I don't know, in Korea, you actually lease the cell phone, right? So like you're renting it, so it's not buying it. And after a period of time, let's say 3 years or 5 years, 5 years for someone, you return it back to the telecommunication company, right? So this is to reduce the cost of collecting end of life phone, for example, because uh, uh, that can be quite expensive. So this kind of new innovative business models can help as well to make the process become more economic. Yeah, so that's just an example. And even, for example, now down to a carpet in your home, I think in Europe, for example, they rent the carpet to you, and when it's broken or at the end of life, they're taking it back and replace it. And but in this case, you still have your materials go back into recycling chain. It's not lost in the in the uh, in the world, and it's difficult to if we want to get that back, or costly basically. Right, there's also aspect about infrastructure and logistic, facilities for pre-processing. In addition to the main extraction processes facilities, you will need to have a good collection system, network of collection, transportation, and resources, and associated costs. Consideration of the size of the facilities, from small scale city based to a large scale integrated smelting and recycling plants. So this one is quite interesting things to note. So it's also different for different countries or different area, right? Like, for example, where you have big land mass in Australia or Europe, for example, where, let's say, the transportation costs via train or trucks not that expensive, then it probably better to have one big large or a few big large scale facilities, and then you ship or you transport the e-waste into one location, one or two locations. But it could also be, for example, you can have a solution as a small scale city-based solution, like a council level or a municipal level, city level. Yeah? So with just processing small scale of this e-waste in that city only, which means that you save the transportation costs because it's within the city. But of course, it's a smaller scale facility, yeah, which means that in that country, or in that island, you may have a different or many small scale city-based recycling plant. That's another options. Or this is also another option here, which is quite interesting because when we did the study, this is something that we consider as well. In the case of, let's say, archipelagic, archipelagic countries or countries that have a lot of islands, such as Indonesia, Fiji, or other countries. So they have many islands, right? So one idea could be also, okay, you have small scale um, um, you know, recycling and metallurgical recycling facilities that you put on a ship, and then it goes into different island, and then you process it on the ship, for example, or the ship just need electricity or whatever. So that also some model, something like that is quite interesting as well. There are non-technical challenges such as government system, governmental policies, legislation that can help promote and drive the market for processing towards alternative resources. Yeah. It provides framework for the development of innovative business models. For example, government can provide incentives. A few years back, there's no, in Australia, there's no restriction in exporting waste PCB, right? Or secondary source or waste battery or something like that. So previously, in Australian perspective, what we did, we just shipped this e-waste to Indonesia, to Korea, to Singapore, and then they process it, right? But recently, in the past 10 years, then there's also a government restriction on exporting this, and government also can provide incentives for the business if they process this e-waste in the country. So that will help with the growth of the business itself, and stopping that export and then processing in the country. Another aspect is social and socioeconomic challenges. For example, education and information flow in the society about recycling and the underlying wealth associated with the above ground waste. So I think these days, this education and information already go through majority of the countries, but still, in the society, we will need to make sure they know, more about this one. So this is not a waste. This is actually resources. It has some value. So we don't want to. We want to make sure that it doesn't go into a um, landfill, but we extract them, we process them, so we put them into recycling chain. Yeah. Some paradigms or cultures within the society can act as a barrier. For example, maybe in some cultures there's no it's very difficult to throw things away, right? So if you have mobile phone, for example, and it's broken and it has some emotional value, it's a memento, right? So you even though it's broken, you don't want to put it into recycling chain. You don't want to throw it away for recycling, so it just stay in your in their cupboard or in the drawer, right? So it just stay there. So that is actually not good because it counted as a loss materials. So we cannot recover the value back from those end of life products. Yeah. So yeah. Okay, so that's still the bigger picture. Now we can go into more direct, more detailed how we process this e-waste. So in general, when we're talking about broader e-waste, there are 3 steps in general, right? Of course, the first bit is collecting this e-waste, yeah. So some government policies, public awareness, and easy access to collection facilities will help this bit, right? So of course, this say it's easy to drop off your e-waste. The e-waste bin can be easily now found in in a supermarket or in store and whatever. So you can easily put that, and that will be transported into the uh, collection facilities, right? So that's the first step. The second step is, we call it pre-processing. So this pre-processing, um, we use different types of processing, mainly mechanical and physical processing. So this is similar method used in physical processing of ores, right? So, and this can consist of a number of things, sorting and dismantling. There's a question whether we should do it manually or automatically, right? There's a trade-off of that one. And then materials liberation, housing of the PC or the product or the laptop, the wiring boards, the drives. So we want to separate them as much as possible, and then we process it mechanically, right? So we shred them, we hammer mills them to make into small fractions, and then we do separations of metals and non-metals. For example, screening, we use magnetic separation, eddy current separation, density separation, and other stuff, right? And these fractions are the one that we process further for end processing. So this end processing usually involve the use of metallurgical processes to recover metals. Yeah, and there are different route. We will look at that one later on, and depending on what the fraction and the materials. So this is applicable to most of secondary resources, urban ores. Yeah, the thing that different, of course, probably in this some slight difference in the pre-processing, for example, and the end processing, but it's all these three major steps in processing of e-waste. Yeah. So this one is an example of flow sheet of recycling of electronic products. Yeah. So the first bit is pre-processing. Yeah, this one here. So this is after we collect them, right? So product collection. So what they do is they test first, if it's still working, could it be, for resale or reuse? So some of them that can be resale reuse goes that line, and then if not, then disassembly, and the part is the part. Some of the part can be reused or resell, and that can go to this one here. If not, it goes into the size reduction or shredding, right? And then we go into this physical, mechanical pre-processing, right? So it could be starting with using vibrating screen, right? For sizing them. Yeah. Some of them go back here for the reduction, right? And so on. And then we separate first the magnetic materials such as ferrous metals or steel using magnetic separation, right? And for non-ferrous metals that has maybe small or light response to magnetic field, we can use eddy current separation. And then for light materials such as plastic, we can separate that by density separation, and then you'll end up with the final residue, which you cannot reuse or anything, and that's the one that goes into landfill or burn in to get energy out of that if still can. Yeah. So usually the circuit boards and batteries are removed during this assembly in that part there, and processed separately or resell or so on. Yeah. And so this is the first step basically. So this fraction here, the ferrous metals, the non-ferrous metals, plastics, this is the one that going to the end processing where we can recover or remelt or recover these valuable metals. Okay, so the physical separation processes, you want to separate the crushed waste PCB or material, right? So there are many techniques. So one can use this automatic technique here, which has a sensor based sorter. So let's say here you have a different colors of green and black, and you have a sensors that detect that different color, right? And as it goes through this belt and go to just about to fall, and we have this air gun to shoot, let's say, the black only um, fraction, so that the black fraction can go into this bin here, and the green one goes into this bin. So this is can be used to separate this black material and green materials, for example, and this is quite automatic. You can use the eddy current separator. Here, the fraction, let's say it's a mix of green, black, and red. So the one that has light response to eddy current will just go all the way here. The one that has a bit more, affected by eddy current goes in the middle, and the one that's strongly affected by eddy current is still stick in the in this rotating belt here, and there's a scraper here which putting the materials into the third bin over here. So this is an example of eddy current separator there. The one using density difference, for example. So this is there are a number of them. There's a cyclone one. There's also rising current separator. So this one here, we use fluid, right? And in here, the green one is lighter, so it's actually going to the top, and it goes through this belt, and then and separated from the mixture. Of course, the red one being heavier than the fluid, it will go down and it goes into the separate belt, and then separate from the green one. There's also cyclone, right? You put the material from the top, and you have cyclone from the bottom. Of course, the one that is light will follow with the cyclone going up, and then separated from the top. The one that is heavy goes directly down. So that's okay. So that's the first bit, or the second bit actually, the pre-processing after we collect them. And the next step is the metallurgical process to recover metals from e-waste, right? So there are mainly three common route, right? Actually, there's another one route called biometallurgy. But that's usually in the laboratory scale, and also not used in industry mainly. So this is what is called hydrometallurgical route, pyrometallurgical route, electrometallurgical route. Right? So hydrometallurgy is actually a process where we use chemical to recover or extract metals. Yeah. So it involves some pre-processing. So it has to be I think I have some slides actually to explain in more details. But in general, it has to be small materials. You need to crush them into very small size. Yeah. So that's the pre-processing is really important there. And then you leach the fraction using chemicals. It can be acid or caustic solution. So we use large amount of chemicals. And then you separate the precious metals from the leachant using solvent extraction, adsorption, or ion exchange methods. So basically in the leaching, you absorb the selected elements into the solution, right? And then the next step is trying to extract that element from the solution using this technique. So this hydrometallurgical route is also common metals extraction process in mineral processing, yeah, in industry, and it's good for a small scale process. There's uh, uh, also a advantage of not uh, um, not need a high capital to make this process work. Yeah? You just need a space and some chemicals, and then you process it. Yeah. We'll see that in more details in next few slides. Okay, next one, there's also pyrometallurgical routes. So pyrometallurgy, from the word pyro, is actually using high temperature. So we use thermal energy, yeah, to aid us to recover the metals. So what's interesting about this one is pre-processing is not necessary for small devices. So for example, in industry, you know, the pre-processing when you crush them, right? Sometimes they don't crush. So they just put the whole battery into the smelter. They put the whole waste PCB about 10 centimeters, which is the big one, go into the smelter, right? So it direct feed into furnace at high temperature. And the key, the simple key process is basically you remove the metal fraction into a molten bath. And then the unreducible, you see, oxide end up in the slag, yeah? And some of the hydrocarbons or coke, hydrocarbons and plastics can replace coke as a fuel and also reductant. That's the in the parametallurgical process. The third one is electrometallurgical process or routes. So this is we applying electrochemistry concept. Yeah. That is, we use electricity to drive the process. Right? So this involves the use of electrodes, where we apply the electricity to, right? And then you dissolve your materials into what is called electrolyte. This electrolyte can be aqueous, it can be molten salt, or it can be molten slag. And then by applying the electricity, right, in the electrochemical system, you actually deposit high purity metals in the electrodes. Yeah. Now this one is quite a slow process in general, and we usually apply this at the very end of process chains to refine or produce high purity metals. Now in industries, they usually try to combine some of this to take advantage of each of the process or to optimize the whole process, as you will see in the next couple of slides. Right, so let's go into details on the first route, which is hydrometallurgical route. So this table showing a different process, a different route for recovering different metals. So classified by leaching agent and also process condition and the types of recovered metals. So now I should mention majority of the materials in this lecture is coming from this paper here. So this is from Halik et al. So Halik was my PhD student, and he's currently an associate professor in, I think, one of the university in Saudi Arabia. So he wrote this paper together with me, which is very nice paper that summarizing these different e-waste processing route and technology, including in industry. And this is coming from that. So if you're interested, you can try to chase that paper. I think I have the details in the next few slides. So for example, Park and Frey, they use aqua regia as a leaching agent, right? But you can also use different types. You can use nitric acid. You can use hydrochloric acid, sulfuric acid, and so on, right? So and the condition is you leach them. You can also use cyanide to leach as well, which is not very good. Yeah, and this is the condition and what temperature, what ratio, and other sort of key observation, and the recovered metals ranging from all, gold, silver, palladium, or gold only, or with copper as well, or trying to extract multi-stage extraction. For example, in this case, you extract thin lead, zinc, and aluminum first, and then second stage copper and nickel, and then the last bit is the silver, gold, palladium, and platinum, for example. So yeah, so in general, the hydrometallurgical route is slow in general, time consuming. So there's an impact on the recycling economy. So when you want to process tons of e-waste, you want to make sure that you process it as fast as possible. Second one is you will need to have quite extensive mechanical pre-processing. So you want to have the size of the waste PCB to a very small for quite efficient dissolution. So you cannot put in the whole bit of PCB. It just doesn't work. So you want to crush it into very fine powder and then put it into the chemicals, and then you get the leach, and you can have the leaching process. Now, there is also a note here. Actually, during that liberation and crushing process, there's some investigators, some researchers have estimated that 20% of precious metals could be lost during that process. So that's small bit of gold on top of the IC, integrated circuit, or on top of a microchip, for example. That, let's say, palladium in the capacitor, during this crushing, that can be lost. So that's not good. There's a loss in the value as well. So there are possibility of precious metal loss during dissolution and also the subsequent steps as well. Now, another thing that is not good about hydro is it leaves behind large amount of residues. So remember, as I mentioned earlier, you have waste PCB or mobile phone, for example, mobile phone PCB, for example, and what was I going to say? I forgot. Waste PCB. Oh yeah. So the elements of interest is only 1% maximum, whatever, or few ppm, like hundreds, thousands ppm. So when you target that elements, you leach it, right? It's only that element that extracted, or maybe a bit of copper as well, right? So it means that you still have about this a lot of plastics and oxides and glasses that needs to be further processed. So that residue is still big, right? And also there's a problem associated with the in the leaching or leaching agent. For example, if you use cyanide is very hazardous and environmentally unfriendly. Halide is corrosive and oxidizing. Thiourea is a high cost, and also the consumption is pretty big. Thiosulfate as well is a high consumption. So these are some of the limitations for hydrometallurgy. This is just more details of some of the process. I think in the table before, in the top one, there's one from Park and Frey. So this is using hydrometallurgical approach for recycling of PCB. So first you have the electric scrap, you shred them and do some magnetic and current separation, mainly to remove iron and steel and also aluminum. And then you go into first solder leach using HBF4. Basically to recover solder through electrowinning and also separate the non-metallic fraction of PCBs. And you have the residue, which is about 18%. It contains some copper, zinc, nickel, silver, gold, and palladium. And then it goes to a second leaching using ammonium sulfate, right? Basically to extract the copper, where the copper is recovered, and then you can use solvent extraction or electrowinning to get that one. And you have the residue again, about 2 to 8% of the total initial, right? It still contains zinc, nickel, gold, silver, and palladium. In here, you try to recover the precious metals, and you'll end up with nickel and zinc at the end, for example, and you can separate them as well, right? So it's quite a long process, but it can have multi-stage sort of processing in there. Now, pyrometallurgical route. So in pyrometallurgical route, we use high temperature to process e-waste. The problem in there is require high amount of energy. So we're talking about temperature up to 1200 degrees Celsius, 1300 degrees Celsius, 1400 degrees Celsius. So around this temperature, when talking about the copper smelting, for example. So the idea is you smelt them in a furnace, right? Or you can also incinerate them or combust or doing a pyrolysis of the waste PCB. Now, in industry, in many industries around the world, including in Korea, usually we try to process waste PCB and embed them in copper or lead or zinc smelter, right? So we use this base metal of copper, lead, and zinc as a we call it a metal carrier, yeah. Uh, um, so and so basically we are concentrating the valuable metals. We absorb the valuable metals into copper, lead, and zinc, and then we then further process that one. So so one of problem with pyrometallurgical route is also it has large capital expenditure for large facilities, and yeah, so it's but big investment, but it usually big return as well, right? So the difficulty is at the beginning because you have to come up with this large capex at the beginning. So I mentioned before also, in industry, they put the whole bit, not crush them. So for example, the waste PCB, put everything of big size, 10 centimeters by 10 centimeters even. Batteries, for example, batteries also just put the whole bit to their smelters. Now, specifically about the waste PCB has some plastics in it, and plastic actually can be considered as a fuel as well, because it has some stored energy and heat value. So these tables and graphs showing us the different heat values of different plastics. So for example, here, general fuel is about 25 gigajoule per ton, the heat value. Polystyrene, about 20. Polyethylene is actually 45. Polypropylene as well. PVC is big. PMMA 45. So I think, and here also showing the composition temperature range, and also the store energy in these different types of plastic or resins in scraps, yeah, in e-waste. So so theoretically, it is there's a energy value there, but of course you practically sometimes it's also difficult. So you need to make sure that it's burned correctly and at the right time, and so on, right? Sometimes you also need to char them as well, depending on the materials. Right, so that's the general process there, and the general process route, and as I mentioned, in industry usually you combine each of these. So it's not just one hydrometallurgy, it's not just one pyro or electrometallurgy, but it is actually a combination of 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 those routes. Yeah. So in industry, usually they use base metal smelting route as the main process, and then they process e-waste into that process. So in terms of copper smelting route, there are a number of companies around the world, industries around the world. I think I should put example of Korea, so I forgot about that one. I think I have another slides talking about plant in Korea, but anyway, so it's so actually processing of e-waste has been done being done in industry, but it's not fully optimized, and we want to have more and more e-waste process in industries. Yeah. So I just want to give some more example. For example, here this Umicore refinery in Belgium. So they process complex materials. So they process dross, mud, spice that's coming from lead and copper smelters, and slimes from copper refineries. Now, these slimes from copper refineries that usually contain these precious metals, right? Because after electro refining, the remaining of the impurities, which is mainly precious metals, it settle at the bottom as a slime, and that contains a lot of precious metals. So they process that one. Um, they also process slag, flue dust, lead sulfates, copper cement from silver, gold, nickel, and zinc refiners. So basically trying to recover as many things from uh, different types of secondary sources, right? Including spent catalysts from oil refining, petrochemical, and other sectors. So that one contain PGM, platinum group metals, yeah, and as well as electronic and computer scraps. So as you can see there, that's the mountain of waste PCB, and you can see that waste PCB is the size of an actual size of your laptop or your iPad, a tablet. So um, 10 centimeters, 15 centimeters. So they just put that directly into the smelter. Right? So now I have actually spent some time in the company Umicore when back in 2016. So that's actually almost 10 years ago. So time flies really well. So I spent about 6 months doing my sabbatical over there to trying to help them also improve the process, and also doing a project over there as well. So 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 their plan basically is an integrated plan where they try to optimize different processes. So there's a copper smelter for copper production. There's also lead blast furnace to process lead. And there's also sulfuric acid plant to process SO2 to produce sulfuric acid. And there's an electrowinning process and so on. So you see this uh, the green arrow, basically the points where materials are added, right? And for example, the e-waste in particular added in the copper smelter there, right? And yeah, and they try to recover different types of elements from different flows, ranging from sulfuric acid, copper, gold, silver, platinum, palladium, uh, rhenium, ruthenium, iridium, indium, tellurium, selenium, lead, tin, bismuth, and also stibbium. This is one from Korea. This is also trying to optimize zinc and lead process with copper process. Yeah, and same thing here. You process the waste PCB in the copper smelter, right? Copper osmotic TSL here, um, and um, and optimize to get as many elements as possible. Right? So, for example, in this case, the lead refinery. In the lead refinery, you process the bullion, and then you get the lead, but there's also lead slime where it contains the bismuth, gold, silver, and indium, and that is processed further in precious metal refinery to get that one. We've got zinc produced in here. What else? Yeah, copper, of course. Yeah. So as you can see, it's a combined electrometallurgy, pyrometallurgy, and hydrometallurgy as well. Well, this is just mentioning in more details about each of the process and the metals recovered from the different industries. For example, just take one here, Umicore, get gold, silver, palladium, platinum, and so on. So the main process is using copper smelting using isosmelt or TSL, and then copper leaching, and electrowinning and precious metals refinery to get the final valuable metals from them, from the resources. Yeah. Right. So now I also want to explain a bit about previous work that we did in Australia. So this is actually thinking about yeah, I think it's also about 10 years ago, roughly. So about 10 years ago, we had what is called Wealth from Waste. So this is a research consortium in Australia, um, where Swinburne, where my university is working with other university, and also CSIRO with UTS, Yale in the US, and Queensland, and also Monash, to trying to understand the electronic waste in Australia and trying to improve the um, uh, improve uh, the recycling system in Australia. So I think we produced quite a good research result that inform the government, and since then there's a significant change in terms of collection, in terms of other things to consider there, in terms of the technology and other aspect. So I just want to quickly mention about what we did in that consortium. So we did a work on evaluating the various existing processes, technologies, and process routes, and then we select a potential process route for Australia that technologically feasible and high potential to deliver big impact and also deliver value, flexible process. Remember, a flexible process is important because it needs to be a robust, and because the input is quite, varies. Economic viable and also environmentally acceptable. Carry out combined thermodynamics process flow sheeting, technomic and life cycle assessment, and modeling of study. So this is the paper number 1, is the one that I mentioned before, mainly that I used for this presentation. So you can look at that one in more detail, and so on. Yeah. So we started with evaluating number of process, and we found that the black copper smelting could be one that is suitable in the context of Australia. So this is an example of black copper smelting, where it has reduction and oxidation process, and then there's a electro refining followed by precious metal refining. So the black copper smelting is more suitable for secondary resources, rather than the plain copper smelting process, which is through when it has sulfide as a resource. But having said that, e-waste can be processed also through that uh, primary copper smelting. Yeah. But in here we're talking about secondary copper smelting, yeah, which is usually to recycle or melt um, copper and copper waste. Yeah. So we try to understand the thermodynamics of this, and so this is just a flow sheet for 38% e-waste input with 100,000 tons per annum capacity, right? And we also investigate the effect of the capacity. So the bigger the capacity, actually giving you more benefit, yeah, right? Total benefit is higher at 200,000 tons per annum capacities. And as you go down to smaller scale, then it's about 10,000 to 20,000. Then you started to get a reverse of the benefits. So if it's still, I think this is still not refined, but we found that in the subsequent study for this one, 10,000 ton per annum is still okay. So it's between 10,000 to 20,000 per annum is still okay, economically valuable. So This one is showing some of our recent work, showing the effect of, when you put in PCB into the process, and you have also copper, you also put copper scrap in the process, right? So depending on the ratio of PCB to the copper, you also can get different types of revenue. Right? So, so basically in here, we found that the gross revenue can be maximized if we have a mix waste PCB and copper of the same amount, 50%, right? So if we have 50-50 in, then the value, total value, gross revenue is about 90 million Australian dollars, and this breakdown per element contribution there. So we also do some key parameters assessment, which one is actually giving quite sensitive effect to the value. So we found in here that so the plant capacity is the one that giving significant effect to the economics. So if it's changed 20%, then it's a significant increase there. And the second one is the price of the products. So for example, here the gold price, right? And then also mainly the gold price actually, and silver price is not that affecting, but still some effect. So if the gold price fluctuates significantly by 20%, for example, increasing 20%, then the revenues can be up to 40 million higher, for example. Likewise, if it's reduced by 20%, then 40 million lower. And this one here, what is that? That is a copper price. Then the third one is copper price, because the copper itself, the amount of copper is quite big, so that gives a significant effect to the economic as well. So that's second. So that's first we talk about the technical, the thermodynamics. Then we next focusing on the techno-economics, but we also try to estimate some carbon footprint, like a small scale LCA analysis. Yeah, it's not a full scale LCA analysis. It's more like carbon footprint assessment. So we develop a different scenario. For example, here. When we have 10,000 tons per year capacity, that's scenario 1. Scenario 2 also 10,000 per year. But for the scenario 1, we have location in Sydney, for example. But in here, what we do is, let me think how I remember this one. Oh, okay. So in here, we're trying to process and recover copper, gold, and silver, right? In the scenario 2, it's still the same, 10,000 tons capacity, but instead of going down until you produce copper, gold, and silver, you just produce the black copper. So that is the copper that is quite impure, but it has, impure means that it has a lot of elements, but the element itself is comprised of the precious elements, gold and silver. So it's not just copper, right? But copper that contain gold and silver. So you can actually sell that as well. So in the scenario 2, we stop at black copper, right? And the scenario 3 is where we have larger capacity, which is 100,000 tons per year, but we produce copper, gold, and silver. And then I think in this case is one big facility in Sydney, and from our Australia, we send that to Sydney, for example. So we found that using that different scenario, there are this detailed number, but I think what's important here is the one on the bottom here. So the total carbon emission per kilogram of copper, right? So in the scenario 1, where we have small scale facilities and recover them until gold, silver, and copper, it gives about 3.76 kilogram of CO2 per kilogram of copper. In scenario 2, right? where we produce black copper and then we sell the black copper, that give us about 3.55 kilogram of CO2 per kilogram of copper. And scenario 3, which is a big scale, right? But one, not many. It's only 1.96. So it's interesting to see that larger scale, maybe 1 or 2, big one, the total CO2 emission is actually the lowest. Yeah. We also analyze if, for example, we use different electricity source, for example, solar, wind, and so on, how that will affect the CO2 emission, right? If we're using from grid, also how much. So, and also from the process itself, where is the total contribution of carbon, the majority of carbon actually coming from. So as you can see from it, different scenario, but mainly the reduction oxidation process, the one that giving the CO2 emission, right? And the mechanical treatment is not so much. The transportation stage is not so much uh, uh, in terms of from the total, yeah. So yeah. So yeah. So having said all of that, I think I want to also um, emphasize is that, okay, so these products actually quite complex, right? And you can see how to process them. It takes a lot of effort, and also it's quite a long process. So I want to emphasize the importance of design for sustainability, right? So in this case, we want to aim basically to reduce environmental impact of a product over its entire life cycles. So we want to make sure that the production of the product itself, we we how do I say it? We make sure that from the design aspect, from the material selection, from the manufacturing process at the end of life, it's is very well thought of, so that it's easy for us to recycle, for example, and across this chain here, we limit the environmental impact, right? So so come that should come from the beginning, from the design aspect. So we want to make sure, for example, the product that we design and produce is easy to dismantle, for example, right? And yeah, it's not easy actually. Yeah. So in terms from the design aspect, for example, the product should be designed for optimum use. Energy consumption during the use should be minimized. Lifespan should be optimized by increasing reliability, durability, and designing for easy maintenance and repair. In terms of selecting the materials for your product, right? We want to make sure that there's no unnecessary materials should be used. The material should be, not harmful to the environment and easily recyclable. And certain intimate combination of materials should be avoided. For example, CREME elements should be limited, as liberation would be difficult. So, so for example, here, this is schematic that's showing, incompatibility of elements. So for example, when you have iron, right? And iron is in intimate, in terms of part, yeah, close by with other metals, such as, let's say, tin, yeah, iron and copper, right? And tin, right? Such as in the refrigerator, yeah. It is not good, because when you have copper goes into the iron, when you remelt them, it's very difficult to remove copper. Same thing, if you have tin and goes into iron, and it's very difficult to remove. So the black one here is the one that is incompatible, unacceptable combination. So you want to avoid, designing your product where you have iron and tin together, iron and copper. The one and the gray one is undesirable, right? The one with the shaded is acceptable. So for example, iron and carbon, iron and chromium is still okay. Iron and nickel still okay. Actually, iron and nickel is very difficult to separate, right? But because nickel is used in iron in production of stainless steel, same thing with chromium, then it is okay. Yeah. So anyway. So right. So I just check the time. I think the time is so I still have some materials, but I just want to check the time. Should I um,
Don't
stop
worry, don't worry.
or
You may go ahead.
okay, just I think there's a few more slides. So okay. So right. So in here basically yeah. So that we were talking about the design aspect, the material selection aspect. In manufacturing aspect, we also need to consider sustainability in there. So, so for example, product should be produced in ways that reduce the quantity of energy, water consumption, and also the emission, right? And at the end of life, which is the context of our discussion, the product has to be either easily refurbished, reused, or easily recyclable, right? So so we think from the beginning, from the design, from the material selection, from manufacturing, end of life, and we can come to the design for sustainability, where you maximize you can you can still get the purpose of your product, but with the minimum impact to the environment. So the question is your phone or tablet meet this criteria? So I think to some extent these days they try to do that, right? So these days the modern cell phone, for example, the part can be easily separated, and as much as possible it's modular, so you can separate them easily and go into different recycling stream easily. Right, so I think this one is this is also some of recent work. I just want to show in here that the solution to recycling of e-waste is not only one because it's quite complex. It will also depend on the each of the location and also depend on the costs and as well and availability of the technology. So this is just showing how we can have a different processing route of e-waste where we have a mobile or substation processing facilities, which is the red one, right? So you can have small scale red facilities here, like the one, but so you can process that in a smaller scale, but also that product coming out from these stages of small scale facilities can also feed into a big one. So the blue box, the big one here, sorry, the blue box is a big integrated smelting processes, right? So so in an ideal recycling system, we want to have everything in here. You have small scale facilities that can process in city wide area, small area, but also can feed into a bigger smelter as well, and so on. So yeah, so we can optimize this process basically, ideally. Right, so I have a few more slides. I just want to show other challenges as well. So I mentioned about there's a lack of fundamental information, right? So for example, there's a limited thermodynamic information about these valuable elements. Yeah. So especially for secondary copper processing. Yeah. So in terms of primary copper processing, there are some data available, right? For each of the metals, but for secondary copper processing, such as black copper smelting, for example, there's only at that time, I think what year is it? This is about 10 years ago. Yeah. There's only one data available for tin and for indium, right? And since then, we in Swinburne we also systematically investigating this thermodynamic information, right? So we started with palladium and germanium and so on, yeah, gallium, and still continuing until these days. So so the way we do it is we actually try to measure what is called the distribution coefficient. That is, trying to understand, let's say, if you have germanium, if you have palladium or tantalum in the condition of black copper smelting, where the germanium and palladium and tantalum will go. Is it going to go into copper? Is it going to go into the slag? Or is it going to go into the gaseous phase? So we do a systematic measurement on that one. So we try to measure that as a function of oxygen particle pressure. So this is the diffusion coefficient, and the thing I mentioned for germanium and palladium at different temperature, and come up with some relation to explain that. So the importance of this is if we have a lot of information like this for different types of elements, then we can optimize the process, by trying to design the conditions and the slag that is suitable, so that you can, operate a certain condition to first, for example, absorb the germanium and palladium first, and then go into different condition to absorb the other elements, for example. So that's the idea. This is also the same thing, but this is for gallium. So our work and other work as well, as a function of temperature and PO2. So bit by bit, we generate data for germanium, tantalum, palladium, and so on. Yeah, okay. One slide. This is the last one. So so as you can see, it's quite a complex situation, yeah. But there's a lot of potential, of course, for processing of these urban ores to support circular economy and get the values from this waste. As I mentioned, there are some technical and non-technical challenges for sustainable processing of these resources. And we have to look at this in a comprehensive way. So so we need to address from different angle, right? Not just from the science or the technological aspect, but also trying to understand or trying to solve or contribute from the social aspect, from the governmental policy aspect, from the economical aspect, and so on. So actually, we need expertise from different discipline, not just metallurgy or materials. Yeah, so and the optimized processing route will depend on a number of things that include of different products will have a different process route, for example, a location, whether it's in Korea, Indonesia, Australia, or Europe, and there are also other non-technical aspects in there. So that's basically the presentation from me. So thank you very much, and yeah, it's